Hello everyone and welcome to part 2 of chapter 1. Last time, we talked about the different types of energies and their formulas, and then we discussed the mechanical energy, which is the sum of the kinetic and potential energies. Now let's talk about the conservative and non-conservative forces. A non-conservative force is the force whose work affects the mechanical energy of the system. So for example, if we have a body in motion and then there is friction present, the mechanical energy of the system decreases over time. This means that this friction is a non-conservative force, whereas a conservative force is a force whose work doesn't vary the mechanical energy of the system, but it can affect the distribution of the kinetic and potential energies that make up this mechanical energy. And as you can see on the screen, I have listed a few examples of conservative and non-conservative forces. Now let's talk about the mechanical energy. If we say that the mechanical energy is conserved, then we know that delta ME, or the variation of this mechanical energy, is equal to 0, because the variation, or delta ME, is equal to the mechanical energy final minus the mechanical energy initial. And if we subtract these two quantities and we end up with 0, that means they're equal, and then this mechanical energy didn't differ between the beginning and the end of the experiment, and so it is conserved. It remained constant. Whereas when we have frictional forces, or as we mentioned previously, non-conservative forces, this mechanical energy is not conserved anymore. It's non-conserved. So delta ME becomes equal to the work done by the frictional forces. Now let's discuss the work energy theorem. The work energy theorem states that delta KE, or the variation of the kinetic energy, is equal to the sum of the work done by the external forces and the work done by the internal forces. But the work done by the internal forces discusses or shows that we've got interaction between the different parts of a system. But if this system is rigid, this interaction is no more, so this work becomes equal to 0. And so the original formula, or the work energy theorem, becomes delta KE equal to the sum of the work done by the external forces only. Now let's talk a bit about the work in general. The work done by a force F, as we can see here, is equal to F dot D. Another way to write this formula would be right here, when cosine the angle between the vectors F and D, as represented here, is theta, basically. It's a different naming. So F is the vector of the force, and the vector D is the displacement of the mass, or the body. And theta here is the angle between the vectors F and D, and we can write it differently as written here. Now for a more specific case, we've got the work done by the weight, which becomes equal to mg h1 minus h2, h being the height. So h1 is the height at the initial specific point, and h2 is the height at a second point. We can also write this formula in this way here, which follows the original formula, F being mg in this case because we're talking about the weight, and the displacement d remains the same. And now for the work done by the tension, it is equal to minus half kx squared. And I've added this picture here because it shows how the tension affects this body, or the motion of this body. So this body is moving to the right in the positive direction. Its displacement is x, and then the tension opposes this displacement, and thus it has a negative, it goes in the negative direction. But now I'm going to give a small note on this part right here. If F and D, so if the force and the displacement D had the same sense, or were parallel to each other, so not like this picture, if they were parallel, then the angle between them is 0. And as we know, cosine 0 is equal to 1. So the formula becomes F dot D, but here the D should be a small letter. And if F and D were opposite to each other, so if this was a straight line right here, and D went like this, and F, sorry, went like this, or vice versa, then the angle between the vectors F and D is in this case 180 degrees. And as we know, cosine 180 is equal to -1. So this formula right here would be minus F times D. And in case these two vectors were perpendicular, then the angle is 90 degrees, cosine 90 is equal to 0, so the work done by the force is immediately equal to 0. Now, let's discuss the internal energy, which is also called the microscopic energy. I'm only going to go over this briefly and quickly. The internal energy, just like the mechanical energy, consists of the macroscopic or the large-scale kinetic and potential energies. The internal energy or the microscopic energy consists of the kinetic energy and the potential energies on the microscopic scale. When we think microscopic scale, we should think of the molecules or the particles that make up this body. I've given here an example. The kinetic energy, the microscopic kinetic energy, or the internal one, can be due to thermal agitation. So if you heat up a body, the particles of this body will be in motion, and this creates the internal kinetic energy. And the potential energy can be due to the change of the phase of the body. So if it's changing from one phase to another, this modifies the internal microscopic structure of the body and thus affects the binding energy of the particles, which creates the internal potential energy. And here, note that the potential energy can have different forms or different types. It could be electromagnetic, structural, chemical, or it can be related to the mass and the nuclear energy. So this is how we can relate it to the potential energy. Now, the total energy and its conservation, let's talk about that. The total energy, or capital E, is equal to the sum of the mechanical energy and the internal energy, which is symbolized by capital U. And of course, in all cases, energy is always conserved. Total energy is always conserved. So energy can neither be created nor destroyed. So delta E, which is the variation of the energy, or the total energy, is equal to 0. If we substitute here in this formula, delta E is equal to delta ME plus delta U, and so they're both equal to 0, so delta ME becomes equal to minus delta U. It's simple. Now for a more practical and visual example on the conservation of mechanical energy and the variation of the kinetic and potential energies. Here we can see a skater on top of a slope or a curve. At the highest point here, we can look at the graph and we notice that the potential energy is at its maximum and it is equal to the total energy, which we call the